In this video, I'm going to be talking about applications of metal alloys. And in particular, I'm going to start by talking about the most popular class of metal alloys, which would be iron-based alloys. So we're going to be talking about steels, essentially, and other iron-based alloys first. And I'll probably break it into several smaller videos for the other metal bases. So the first distinction we have to make when we're talking about different grades of material is cast versus wrought alloys. And the idea here is that if a particular alloy is formulated such that it is to be cast and then subsequently worked into a particular shape, then that's what we call a wrought alloy. Cast alloys essentially are just too brittle to actually allow that deformation. It's not that they're not useful, it's just that they're meant to be cast in a particular shape and then maybe just machined, do some finish machining. But you wouldn't be doing any drawing or any forging on a cast alloy. So you'll usually see the different grades broken out between wrought and cast. So ferrous alloys, when we look at ferrous, we're saying things that have an iron base to them. And when we're classifying an alloy, we typically classify it based on whatever element is the most plentiful. So iron-based or ferrous alloys are going to be those where the majority of the material by mass is iron. And we can break these down into steels, which have a little bit of carbon, and then cast irons that have a lot of bit of carbon. And then within the subset of steels, we can talk about low carbon steels, medium carbon steels, and high carbon steels. And each one has their place and their usefulness. If we switch and instead talk about high alloys, so we're talking about generally in the range, we're talking about alloying additions 5, 6, 7% and above. Those generally get shifted into a class of steels called high alloy steels. And tool steels fall under this category, and also stainless steels and a lot of iron corrosion resistant alloys would fall under the category of high, or under the classification of a high alloy ferrous alloy. Yeah, these are the most abundant. This is the majority of the materials that we build out of. So it's important to know a little bit about them. The numbering scheme, it depends on sort of where you're working, but the American Iron and Steel Institute and SAE, Society of Automotive Engineers, their numbering system is the most popular in America, and the typical scheme is that the first two numbers tell you sort of what else is in there besides iron and carbon, and the last two digits of the four digits are dedicated to telling you the weight percent of carbon that's present. So a 1020 steel would be a plain carbon steel. It doesn't mean it doesn't have anything else into it, but it doesn't have too much else. You know, it's got some manganese in there, but not significant additions. And then the 20 would tell you that it's 0.2 weight percent carbon. So if we're talking about, let's say, a 4140, that would be down here. And we'd say, okay, 41, it's going to have chrome and moly in it, in addition to iron and carbon. And a 4140 is going to have 0.4 weight percent carbon. 43 series are going to be nickel chromoly alloys. And you can see there's a whole bunch of different grades that exist. Sometimes the four parameter turns into a 5 parameter, but you can always just pop open this chart and figure out what exactly you're dealing with here. Some of the most common are your 4300, 4100, 4400 steels, and those are going to be your quenched and tempered low alloy steels. Another numbering system that's a little more popular overseas is going to be the UNS, Unified Numbering System. And so the Unified Numbering System is just basically, it's an attempt to try to standardize across, countries, because a lot of these steels are made in Germany and Japan and other countries. So we kind of want to all talk the same language, and when we call out a specific grade, we want to be all on the same page about what exactly is supposed to go in it. So a lot of times you'll see the AISI SAE designation and then a UNS designation along with it. A lot of times they have similarities as well. So this just kind of shows you what they are. So you can see in terms of our UNS specifications, our iron alloys actually have a whole bunch of different UNS letter designations. So D, F, G, H, J, K, S, and T are all iron-based alloys. And so UNS kind of designates them a little bit differently. But for instance, if you just draw your attention to nickel alloys, are always gonna, their UNS number is always gonna start with an N. So if you see an N, you know it's a nickel-based alloy. Steels can be a little trickier. This is another example of just Google it, look up what you're dealing with when you see a grade that you don't know anything about. So first we'll talk about our steels, and that's iron plus some other elements. Usually we're dealing with less than 1 weight% carbon, except in really unusual high carbon steels. Plain carbon steels, it's iron, carbon, we have manganese, and then residual impurities. And so the manganese is generally balanced with the amount of sulfur impurities that are in there. And the idea here is that we want the manganese to gobble up the sulfur and form manganese sulfide before iron has a chance to combine with sulfur to form iron sulfide. Iron sulfide is way worse for our mechanical properties and our corrosion resistance than manganese sulfide. So it's really just a balancing act there. Our alloy steels are generally going to have elements added in higher concentrations. So our low alloy plain carbon steels, except for manganese, we're not putting anything in there. It's just whatever's in there is residuals that we couldn't get rid of. It's essentially impurities. Yeah. So talking about low carbon steels, if you hear the term low carbon steel, you're talking about steels which have a carbon content of less than about 0.25 weight%. So 1020 would be an example of a low carbon steel. These tend to be very, very ductile and tough, easily weldable, which is actually very important. But they tend to be lower on the strength side. So our yield strengths tend to be less than 40 KSI. The plain carbon versions are not heat treatable. So if you hear non-heat treatable steel, basically all that means is we can't practically form a significant fraction of martensite. So we know when we quench and temper steels, the whole point is to try to form as much martensite as possible and then temper it. So our 1020 steels, you can heat them up, austenize them, and then dunk them in a tank of water, and they're not going to form martensite outside of a little bit on the surface. The target cooling rates that are required to form martensite are just, they're too fast. They do strengthen with cold work. Typically, these have a mixed ferrite-pearlite microstructure. So when we polish them up, etch them, we'll be looking at ferrite grains and pearlite colonies. Since we didn't actually add anything to these plain carbon steels, they are really cheap. So I think one of the more popular grades of low carbon steel that you come across is A36. So it's ASTM is the group that writes the standard that governs the material, and then 36 represents 36 KSI yield strength. So when you go down to Alaska Steel and you buy some random steel products, if you don't ask for anything special, you're probably getting A36. Another important class of low alloy steels is this group called high strength low alloy, or HSLA steels. And so HSLA steels, there are additional alloying elements that are put in there on purpose. but generally they're pretty low weight percent. So when you total them all up, they're almost always less than 10 weight percent, which typically you'd say, I'm not sure if that classifies as a low alloy steel anymore, but whatever. That's what they call them, high strength, low alloy steels. And they can be heat treatable, either by precipitation hardening or by quenching and tempering. And that really depends on the grade. And these HSLA steels typically can achieve higher yield strengths. So we're able to get yield strengths up to about 80 KSI, particularly the ones that are heat treatable. And the other key component of HSLA steels is that they have better corrosion resistance in atmospheric conditions. So it is very, very popular to use HSLA steels in structural components. If we're talking about wide flange I-beams for for a structure and it's going to be exposed to some atmospheric conditions, a lot of times we'll go to an HSLA steel. They're actually also called weathering steels. We'll go to an HSLA steel rather than like an A36, a plain carbon steel. And from your perspective, if you put one of these HSLA steels outside, it would still look rusty when you came back. The difference is that the addition of the copper, vanadium, nickel, and moly, it doesn't make them stainless steels because they're not, they don't have the elements to be considered stainless. However, when added in small quantities, they make that oxide layer, the normally just garbage, non-protective iron oxide, they make it a little bit better. And as a result, when you look at these HSLA steels after they've been exposed for a while, you say, oh yeah, there's a little bit of rust on the surface, but it's generally a nice uniform rust. It's a lot of HSLA steels, people even think it kind of has this sort of industrial look to it, but the idea here is that the corrosion rates on them are significantly less than your carbon, just plain carbon steels. And so if you're going to build a steel structure outside and you're comfortable with it, getting a little bit rusty, having that sort of industrial chic look, you're going to go for HSLA steels. The additional almost double yield strength means that you'll be able to do more with less, right? Your sections will be able to be smaller. So yeah, plain carbon, generally when we're not worried about having insanely high strength or corrosion resistance, and then HSLA or weathering steels when we're looking for a little bit higher strength and we want some corrosion resistance, but not as much as stainless steel, but better than carbon steel. And this just gives you an idea of some of the steels that are available. This is by no means an exhaustive list, but it gives you hopefully a feel for what we're talking about. So if you look at A440, which again, that's going to be an ASTM grade HSLA steel, you can see what's actually in there, right? Low carbon, but you've dropped in 0.3 silicon and the important one, 0.2 copper. And that seems like a very small amount of copper to have to add, but that small amount of copper will actually produce a material that weathers considerably better. And then over here, we just have an idea of what you might use these for. So I'll let you you can review that on your own. All right, so if we step it up now and we talk about medium carbon steels, they fill the gap between 0.25 weight percent and 0.6 weight percent carbon. And we know these tend to be higher strength, but every time we get a gain in strength, a gain in our yield strength is generally accompanied by a loss in ductility, right? They're going to be more brittle. They're almost always produced in a way that they are heat treatable. They're not always used in the heat treated state. So when you buy a medium carbon steel, you'll buy it in a lot of times in the fully annealed or normalized state. So it hasn't been quenched and tempered. It doesn't consist of tempered martensite yet. If you want high strength, you're going to quench and temper it. If you favor the ductility, then you may use it in the normalized state. But again, you're trading off. You're essentially paying for medium carbon steel, but you're saying, I like the higher strength I can achieve. Maybe I can get 70, 80, 90 KSI, but I don't want to heat treat it because I know I'm going to give up ductility in order to do that. The plain carbon versions are going to, I say they don't harden readily, but realistically, if we're talking about forming martensite here, it just means a lot of times you're going to have to do a water quench. You're going to have to do a more aggressive quench. However, the heat treatable medium carbon steels, and I would argue the plain carbon medium carbon steels are still heat treatable. You can quench and temper them. It's just you're not going to be able to do it with really thick sections because you won't be able to achieve the critical cooling rate that you need at the center in order to form martensite. But we know that we've got a whole bunch of medium carbon heat treatable alloys, and this is our 4100, 4300 series that have chrome, nickel, molybdenum additions, and those additions essentially make it easier for the material to form martensite. So our critical cooling rate goes down. We don't have to cool it as fast on our quench in order to achieve that 100% martensite. Once we have the 100% martensite, we of course can temper out the material and dial in, essentially exactly what yield strength we would like for our material. So those are kind of the two different classes. So I think I give some examples here. 1040 is the classic example of a plain carbon steel, and plain carbon medium carbon steel. And then 4340, you can see 4063. And so you can see all of these applications are generally applications where you say, one of two things. Either we are looking for a material that is very hard and therefore has good abrasion resistance, and or we are looking for a material that is can be quenched and tempered to be very strong. Meaning we're looking to essentially have a material that can hold a significant amount of load in a relatively small section. So bolts, a lot of our fasteners end up being medium carbon steel. You can see 4340 aircraft tubing. So I think most of the Cubs are 4340 steel tubing. So obviously in those applications, we're going to need high strength and we're going to want, really strong tubes, but we don't want to have big, thick cross sections because if we're trying to fly, the strength to weight ratio becomes really important. High carbon steels. So high carbon steels go everywhere from 0.6 weight percent up to 1.4 weight percent carbon, although generally they're below 1 weight percent. And these are going to be the hardest, strongest steels that we can have. A lot of times we're using them not necessarily to hold a significant amount of load, but we may be using them just for their wear resistance. So we maybe have some sort of rubbing going on between two components, and we want to make sure the amount of material that's removed over time is relatively low. They tend to be the least ductile, the most brittle. They tend to hold a sharp edge. So if you're into making blades, high carbon steels are going to pop up on your list. Then this is always the trade-off, especially if you talk about knife making, right? That when we take a piece of high carbon steel and we form it into a blade, we want it to be hard and strong such that it retains this sharp edge. But at the same time, you don't want your knife blade to just fracture if you bend it a little bit. So we need to maintain enough ductility. And we know this is always a trade-off. You're trading strength and hardness for ductility, and you have to figure out how much you can trade and still have it work in your application. So our plain carbon steel is almost always quench and tempered. Our tool steels can be quench and tempered, or sometimes they're not. So our tool steels, we're going to be adding chrome, vanadium, tungsten, and molybdenum to. And the idea here is actually we add enough of these elements that they will combine with the carbon to form very hard carbides that precipitate out. And those hard carbides are what reinforce the metal and give it good strength and wear resistance and edge retention. So they're called tool steels for a reason, right? We're generally making tools out of these steels to cut weaker, softer steel. this gives you an idea of what these designations look like. The AISI number kind of totally changes for tool steels, and so it leads with a letter and then follows by a number. So if you see any of these, right, those are tool steels. UNS would have a T designation out front standing for tool. And you can see some of the additions, for, especially for M1, we're talking 8.7 molybdenum. So these are almost exclusively used for making tools. Stainless steels. So we know from the corrosion unit, from what we just talked about, that stainless steels are steels that have more than 10.5 weight% chrome. And we know that that chrome is critical for combining with iron and nickel and forming a passive film on the surface. So if nickel's not there, it'll just form the passive film with iron. And that passive film, we learned, was essential for imparting corrosion resistance. Again, I'll mention this. We're talking about very, very thin films. We're talking about nanometers thick. And that's why the stainless steel fridge that you have looks almost identical to if you took just a plain piece of steel and you just cut it and polished it down. That's how your stainless steel fridge looks, right? Because you can't see this passive film, right? You can't see the passive film. It's there protecting your stainless steel fridge or your stainless steel cutlery, but you don't see it. It's essentially transparent and it's so thin. But it has a significant impact on the corrosion behavior of our steel. So our carbon depends on which type of stainless steel, and I'll go through all the different types of stainless steel that you're dealing with. But it's typically between 0.3 weight% and even up over 1 weight%. We have a whole bunch of other alloying elements, and I'll talk at least about some of the alloying elements and sort of why they're in there. Others I'll just leave to a future discussion. Yeah, so at most, this is good to remember that stainless steels account for 1.5% of the total steel produced by weight. So even though we think of stainless steel as being very readily available, we see it a lot throughout our lives, you also have to recognize that in terms of how much of it is produced by weight, it's a very, very small percentage of the total steel production. So think about, in your head, you should be thinking, wow, that means that non-stainless steels, there's a lot of that stuff being produced comparatively. Stainless steels that contain a lot of nickel tend to be really expensive. Molybdenum is also very expensive, but nickel in particular, as the nickel content of our stainless steel increases, the metal itself, the alloys become more and more expensive. And the main reason that nickel is expensive is actually it's because the market for nickel is very volatile. In general, the places we find nickel, where we mine nickel ore, are areas that are sort of high conflict regions. And so they tend to be a little bit less stable. And as a result, the market tends to swing a lot more. And the producers of these stainless steels, because the market swings so much and the price varies so much, they just pass that cost on to the customer. So the high nickel stainless steels are going to be really expensive. So there is a push to reduce the amount of nickel in stainless steel. And so when I talk about 200 series stainless steels, essentially what we found is we can get the same microstructure and we can actually substitute some other cheaper elements for the nickel. And so that's what 200 series stainless steels are all about. And that's all about the money. So when we're talking about stainless steels, there's a few different designations that we use. There's a numbering system that we use, and that's going to be either 200, 300, or 400 series stainless steels. And then we can also classify them by their primary microstructure. So we have austenitic stainless steels. So the primary structure is austenite, FCC. We have ferritic stainless steels, and the primary structure there is going to be ferrite, BCC. We have martensitic stainless steels, which we know are going to be martensite or more appropriately tempered martensite. And then we have duplex stainless steels, which are a very interesting class of stainless steels that are about 50% austenitic, 50% ferritic. And then finally, we have precipitation hardening stainless steels, and they just essentially gain strength by precipitating certain components out. So they are, sometimes we'll combine them too. You can have a martensitic stainless steel that also precipitation hardens. So we can combine them, but those are the general classes of stainless steels that you'll see. As a rule, if you see pH anywhere in the designation, just remember that stands for precipitation hardening. These tend to be pretty high strength. They tend to be expensive. So if you see the pH, you're going to pay for it. So we know most people probably understand that stainless steels are used extensively. I'm sure you know of many examples of stainless steels being used around you in the kitchen, architecture, all over the place. So they're very, very popular. And I'll go through each of the different classes and kind of give you a little bit on them. I'll try to move a little bit more rapidly and kind of hit on the key points here, and you can go back later and kind of dive in a little deeper if you want. So our austenitic stainless steels, they have an FCC microstructure. In terms of austenitizing elements, so all we're trying to do when we want to form an austenitic stainless steel is we need to drop the temperature at which austenite transforms to ferrite down low. We need to drop it low enough that at room temperature, we're going to have a stable, austenite is going to be stable, which we know is not the case with our plain carbon steels. So nickel does that, manganese does it, and nitrogen does it. And so our 3000 series stainless steels, we predominantly rely on the nickel additions to stabilize the austenitic microstructure. And then in 200 series stainless steels, we rely on a combination of manganese, nitrogen, and nickel to stabilize the austenitic microstructure. The advantage of the 200 series is we're putting a lot less nickel in there, so it's cheaper. Since it's an austenitic microstructure, it's quote-unquote non-magnetic. We know that's not a real thing. What it means is that we don't have ferromagnetism, and so it doesn't have a strong magnetic response. They tend not to be heat treatable, and they work harden as we cold work them. These are the highest produced type of stainless steel. One of their primary advantages is that since they have an FCC microstructure, they stay ductile at very, very low temperatures. So all of our cryogenic components, any component that's going to be holding liquid nitrogen or operating at very low temperatures, austenitic stainless steels are sometimes the only financially viable choice for structures to contain and operate at these temperatures. The trade-off is that they are not very strong. So you're going to need thicker sections in order to accomplish the same thing. They are susceptible to localized corrosion attack. And in particular, chloride-containing environments or halide-containing environments tend to be the ones that cause austenitic stainless steels problems. So when you go out, if you start designing with austenitic stainless steels, always keep in mind what sort of environment is this going to be operating in? Is it possible that there are chlorides present? And fluorides would get you in trouble too, but chlorides are maybe or maybe not obviously the most prevalent in typical engineering situations. Anywhere near the ocean, you're going to end up picking up chlorides. So seawater, saltwater applications, chlorides can cause problems for us. And sort of the Achilles heel of austenitic stainless steel, chlorides can cause pitting, but usually what we're more concerned about is going to be stress corrosion cracking. And so these chloride ions kind of enhance the stress corrosion cracking of austenitic stainless steels. And so remember that stress corrosion cracking, we have a static tensile load. So in this case, we would be pulling this way and that way, right? And we essentially expose it to an environment that may or may not have chlorides, but if it does have chlorides, the stress corrosion cracking is going to be a bigger problem. No cyclic load, static load, and yet it cracks and it fails. So if you see SCC, it stands for stress corrosion cracking, and you are going to be very concerned about what grade of stainless steel you're using if you're handling seawater or any sort of solution that has chlorides in it. As the temperature of the solution that you're handling goes up, the prevalence of stress corrosion cracking goes up. So if you're handling seawater at room temperature versus seawater at, I don't know, 100F, you're going to need essentially an alloy, an austenitic alloy that has a higher chrome, higher nickel content, and it's usually nickel actually that really helps you in terms of your stress corrosion cracking. So yeah, you're going to have to alloy up, and so yeah, that's about where I'll leave that. The other problem with stainless steels is this thing called intergranular corrosion. And so intergranular corrosion essentially occurs when carbides form at the grain boundaries. So we know that chromium is really important to the protection of stainless steels. As it turns out, there's kind of a temperature danger zone that austenitic stainless steels, that if they're exposed to, their chromium will combine with the carbon and it'll form a chrome carbide. And the chromium carbides will drop out at the grain boundaries. And if you think about it, in and unto itself, we're not, I don't know, you may not be too concerned. You may say, well, what's the big deal? But essentially what you're doing is you're depleting the volume immediately adjacent to the grain boundaries of chromium. So what you're doing is you have chrome carbides, but then in the region around where the chrome carbides form, this doesn't look like stainless steel anymore. It looks like just regular old plain carbon steel because you've depleted out the chromium. And as a result, what ends up happening is when you expose it to a corrosive environment, the attack occurs right at the grain boundaries, exclusively at the grain boundaries. And you can see it right here. This picture is a perfect example of intergranular corrosion. Then when you look at that, you say, well, those look like grains. Well, they are grains, right? And the attack occurred very locally, only at the grain boundaries. And you might say, well, okay, what's the problem? We didn't remove that much material. Well, this area right here is done. Right? This whole area of material is no longer bearing any sort of load. So the analogy would be if you want to take out a brick wall, should you find a chemical that dissolves the bricks or find a chemical that dissolves the mortar, right? And apples to apples, you want to find a chemical that dissolves the mortar, right? Because it's way easier to just dissolve the mortar between the bricks. The wall will still come down, and it'll come down faster than if you used a material or chemical that dissolves the brick. So those are the two that we worry very much about. As I mentioned, intergranular corrosion occurs because we stay too long in a temperature danger zone. And so not surprisingly, intergranular corrosion usually occurs after we weld the stainless steels together. So when you're welding stainless steels, particularly austenitic stainless steels, you have to be very careful in basically how you weld them, how long you spend at a particular temperature, because you don't want to let these chrome carbides form. Or if you weld them in such a way that they do form, you need to know about it so that you can take that weld and after the fact heat it up, right? Dissolve out the chrome carbides and then come through the temperature danger zone very quickly so that they can't reform. So welding becomes, this is generally when we're going to form we're going to get our intergranular corrosion. It'll be in the heat affected zone of the weld. And so it's usually we're looking at a post-weld heat treat. We're going to have to treat the stainless steel after we've welded it to avoid intergranular corrosion. In terms of our stress corrosion cracking, particularly in chlorides, what we find is that the more nickel that we add, the more resistant the stainless steel gets to cracking. So as you can see here, this kind of gives you the idea of, this is a really aggressive test, but they use different weight percent nickel stainless steels, austenitic stainless steels, and they put them in a really aggressive chloride solution and figured out how long it took them to crack, to fail by stress corrosion cracking. And as you can see, there's kind of this cutoff here, which unfortunately is at a very high nickel content, where you won't have any cracking. So if you put enough nickel in there, your alloy will become completely immune to chloride stress corrosion cracking. But we know that nickel is really expensive. So if stress corrosion cracking is what's going to kill your stainless steel, you're going to have to play the game to figure out how much nickel you're going to require based on chloride content, based on temperature, to prevent stress corrosion cracking. And obviously, if you get it wrong, it's going to be a problem. This gives you some of the standard stainless steel grades. You're going to see 304 pops here. That's your plain Jane stainless steel. Some of you may be familiar with 316. That's a little bit of a step up, right? And then you also see 316L. So the L designation means low carbon. Now, low carbon means lower strength. But if there's less carbon, then it decreases our intergranular corrosion. So it makes it more easily welded. Basically, we increase the weldability. And that's the idea. So if you're worried about forming a intergranular, what we call a sensitized microstructure, one that's gonna, have intergranular corrosion, with 316, you might buy a 316L, give up a little bit in terms of the yield strength, and make it more easily weldable. These give us, once we get to the more expensive alloys, we start getting into a lot of trade names, but this just gives you an idea of a lot of the different austenitic grades that are available. Nice little flow chart from the ASM manual. Again, I like this because it gives you a little description of what it has and why it has it added, but I'll allow you to go through and kind of browse some of these at your leisure. Ferritic stainless steels are going to have much lower nickel. So we're going to have very low nickel, which is good from a cost perspective. They're going to have a little bit more, they're going to generally tend to be higher on the chrome. These are 400 series stainless steels. So if you hear 400 series, it's a ferritic microstructure generally. Actually, that's not true. I think Martin-Zittick are also 400. They are magnetic because the primary microstructure is ferrite. They have good ductility formability. They work hardened, but not like the austenitic. Their toughness is limited at low temperatures, right? We know they're BCC. We know they're going to have a transition temperature. So you got to be careful if the temperatures get too low. They generally have poor hot hardness or high temperature strength compared to the austenitic grades. So they're also not ideal for high temperature applications. So whereas our austenitic stainless steels generally tend to be pretty good in low and high temperature applications, ferritic stainless steels are not really good in either of those. They're good at mid-range temperatures applications. So yeah, a lot of them have, if we put enough chrome in there, we can have excellent corrosion resistance. And in particular, they don't respond as poorly. They're not as susceptible to stress corrosion, cracking, and pitting in halide environments. So remember, halides, the primary one we're talking about here are chlorides. So if we have a chloride environment, a ferritic stainless steel might end up being a better choice for us than an austenitic grade of stainless steel. This gives you kind of an idea of what's available. 430 is a typical plain Jane ferritic stainless steel. Yeah, this gives you an idea. These are some of the non-standard grades and sort of what's in there. And I guarantee you each one has, there's a reason for each one. It has a typical application for which it was developed. Again, this kind of gives you the flow chart, gives you an idea of why we're adding what. Our Martin-Zittick stainless steels. So we said we can have Martin-Zittick stainless steels, and the whole point of them is to be quenched and tempered, right? So Martin-Zittick stainless steel, we're intending to form martensite through a quench and then tempering that after the fact. As a result, we see higher carbon content. A lot of the excess carbon forms carbides. So a large portion of the stainless steels that are used in blade making are going to be of this class. They're going to be Martin-Zittick stainless steels. Generally, we're trading strength for corrosion resistance. So we're giving up a little of our corrosion resistance, or a significant amount of our corrosion resistance, as compared to the austenitic stainless steels, in exchange for a higher yield strength, higher hardness, and better wear resistance and edge retention. These Martin-Zittick stainless steels are also 400, so both ferritic and Martin-Zittick stainless steels fall into the 400 series. They are magnetic. They're heat treatable. Yeah. Again, one of the flip sides in terms of our actual manufacturing and our fabrication, that welding is trickier. It's not impossible, but the weld procedures get much more difficult than, less heavily alloyed stainless steels. So that's your trade-off, right? Good corrosion resistance, but not particularly easily to fabricate. So high strength, limited ductility. These tend to have the lowest corrosion resistance. So ferritic stainless steels and austenitic stainless steels tend to have much better corrosion resistance, but they have just pretty abysmal strength characteristics. So one example would be 13 chrome, which is used extensively in downhole applications. So we're talking about oil and gas, right? So a lot of the tubulars, a lot of the tubing and casing that we use down underground when we're drilling wells is made of 13 chrome, which is a super martensitic stainless steel. And you might say, well, isn't that a really corrosive environment? Well, not really. If you think about it, more down in a reservoir underground, there's not that much oxygen down there. And so generally it's being exposed to drilling mud and very limited oxygen. A lot of times it's hydrocarbons, not as much water. And if hydrocarbons are not a good electrolyte, so they're going to tend not to be corrosive. That's your oil. But yeah, the limited oxygen thing is a really big determining factor. That the downhole environments are not particularly aggressive in terms of corrosion, but we are generally requiring a material that has a high strength, right? We're going to be suspending casing from, for thousands of feet. And so we essentially need materials that have sufficient corrosion resistance and high strength. And that typically falls to martensitic stainless steels. Sometimes we'll add a little bit of nickel. It'll help improve the corrosion resistance a little bit. But usually the primary reason to use martensitic stainless steels is their mechanical strength, and then secondary is their corrosion resistance. This gives you an idea of some of the martensitic stainless steels grades that are available. 403 is kind of the plain Jane one, and then the price and the mechanical strength kind of goes up from there. These are some of the non-standard grades, trade names, and here's your chart from the ASM manual. Duplex stainless steels. Duplex stainless steels have become more and more popular recently, and they're very, very popular in oil and gas. So the microstructure of a duplex stainless steel consists of both ferrite and austenite. So we get a duplex structure. There's two microstructures, and usually what we're shooting for is 50% austenite, 50% ferrite. And I won't get into how we actually get this to form, but the big take home for you is that we get a lot of the strengths of the individual austenitic and ferritic stainless steels, but we don't get a lot of their weaknesses. So we kind of get the best of both worlds. It's kind of like a composite, a metallic composite. The yield strength is usually about 2x or more of that of austenitic grades. So that may not seem significant just right off the bat, but if you think about it, that means everything you build out of a duplex stainless steel is going to be half the weight of what you build if you built it out of an austenitic or a ferritic stainless steel. The corrosion resistance tends to be similar or better than austenitic grades. So bonus there. Duplex tends to be more resistant to stress corrosion cracking in chloride environments. And if you think about it, it kind of makes sense, right? Because we know austenitic stainless steels that's their kind of Achilles heel. They're going to crack. But now we've got a whole bunch of ferritic stainless steel that's resistant to stress corrosion cracking, that's standing in the way of a stress corrosion crack that's trying to propagate through the material. A lot of trade names end up showing up here. So we're talking about duplex stainless steel. You see a lot of trade names. They tend to be expensive. Usually they're differentiated between regular grades and then super grades. So if you hear super duplex, it just means more chrome, more molybdenum, right? More money is one of the things it means. So LDX, Xeron is a popular, Xeron 100 is a popular duplex stainless steel. 2507, that's a super grade. So I think both Xeron and 2507 are all super grades of duplex stainless steel. Yeah, 2205 is kind of your plain Jane. That's sort of your plain Jane duplex. So that would be a regular duplex. And you can kind of figure out where the numbers come from. The 22 is the chrome, and the 05 is the nickel content, right? That's not the only thing that's in there, but that's what's available. So 2507 is super duplex, 25 chrome, 7% nickel. There's always a reason for the numbers. You just have to figure out what they are. Yeah, these have become, I would say, insanely popular amongst oil and gas because they're relatively cheap, relatively strong, and have really solid corrosion resistance. The last class of stainless steels is precipitation hardening stainless steels that generally have that pH designation. They can be austenitic or martensitic matrix. We can do either. Obviously, a martensitic matrix would be a higher strength. Austenitic matrix would be a lower strength. But in addition to the martensitic matrix, we're going to have these precipitates that form. And so generally what you're going to start seeing showing up here is going to be copper, aluminum, and titanium. So those are the elements that we're going to add in order to encourage the formation of these precipitates. And so we know that that's going to increase the strength of our steel, and that's what we're looking at. So we're usually seeing very, very high strengths in precipitation hardened stainless steels, right on par with the high strength quench and tempered regular steel. And we're still seeing moderate corrosion resistance. I like this. This plot kind of summarizes, gives you an idea for mechanical strength-wise, kind of gives you a comparative analysis of the different alloys, some of the common alloys that are used, right? And so here's your 300 series austenitic stainless steel 316. You can see it has a 30 KSI yield strength, right? And this is what I was talking about. If we go to a 2205 duplex, we more than double the yield strength. If we bump up to a super duplex, we go up to 80 KSI, right? This would be just a carbon steel here. You've got a plain grade 2 titanium here. This is another austenitic 254 SMO is a highly alloyed austenitic stainless steel. And then you can see down here our copper, nickel, and alloy 825 is a nickel alloy. We're talking about relatively low strengths here. So, you know, you got to kind of consider, well, how much load is this structure going to have to carry? How much is weight important? You know, what are my size restrictions, right? And that all factors in to our decisions. Precipitation grades, they can go up to 240 KSI. So precipitation hardened stainless steel can get up to 240 KSI yield strength. So you're talking some seriously high strength steel at that point. It's still not the highest, so we'll talk about the highest in a bit. And so here is the superstar of the steels, and that's Mar-Aging steel. And Mar-Aging steel, it's a combination of martensitic and aging steels. So we know that aging, the term aging, is kind of reserved for precipitation hardening. So when we talk about aging, we're going to be talking about forming precipitates, and then it's also going to be martensitic, but it's a different type of martensite. So it's very important to understand this, right? This Mar-Aging steel is very, very expensive. It's used almost exclusively in sort of defense or essentially really high strength applications. And I'll talk about how high the yield strength goes. It gets pretty insanely high. So aerospace, I know they make the hooks that on aircraft that land on aircraft carriers, the hooks that come down and grab the cable, that's Mar-Aging steel. So we see this in a lot of aerospace and defense applications. I believe it's still export controlled. So if you buy this stuff, the federal government wants to know essentially exactly what you plan to do with it, and they want to make sure you're not going to ship any of it to Iran or anywhere else where we don't want stuff like that to go. So just to give you an idea of how kind of cool and interesting and valuable this material is. So it's an iron nickel alloy. We'll add cobalt, molybdenum, titanium, and aluminum as well. Remember that the titanium and aluminum, generally that's going to be, we're going to try to form precipitates with that. The iron nickel system is very different than the iron carbon system. So when we transform, when we quench our material and we transform, actually I think it'll air cool to iron nickel martensite, right? So we just air cool. We don't even need to quench it. We just air cool it. It'll form this iron nickel martensite. And you say, well, okay, what's iron nickel martensite, right? Iron nickel martensite is essentially we have a similar idea of, oh, it's a super saturated solution, except the transformation occurs, it's still displacive, right? So just like our regular martensite, where we don't allow things time to diffuse, and so we end up with this kind of stretched structure, we also get that with iron nickel martensite. The difference is that iron nickel martensite is actually quite ductile. So it's extremely hard, extremely strong, but it's also ductile. So whereas iron carbon martensite, we know that it's very, very hard and very strong, but it's also insanely brittle. So it's way too brittle to actually build anything useful out of it. Iron nickel martensite is actually quite ductile. And so we end up with this duplex microstructure, and we get, alpha plus gamma. And so alpha is going to be this, precipitate, and we're going to have no perlite or carbides in any of these. So what we're going to end up with is this iron nickel martensite, and it's super saturated with these other alloying elements, which are more expensive than carbon, but rather than carbon. So the carbon's going to actually be relatively low, limited. It's got a BCC crystal structure, and again, the big take home is it's going to be tough, not just strong, but tough. Now, here's the question: how high does the strength go? We're talking up to 350 KSI after your heat treatment. And the heat treatment's very straightforward. The heat treatment compared to quench and tempered steel is very easy to heat treat this. You're not worried about warping. You're not worried about anything like that. So it heat treats like a dream. 350 KSI. I mean, that's 10 times what our plain Jane structural steel is. So this is pretty intense. As we harden this material, right, we're going to form this fine dispersion metallic particles. And so basically we're going to have nickel and cobalt and molybdenum containing particles that drop out and make our material even stronger. They're going to reinforce our material by precipitation hardening. We can weld it, we can machine it, unlike our quenched and tempered alloys, right? And you're always going to do your welding, your machining before you heat treat it, right? You're going to get it in the softest state you can, the fully annealed state, do all your work to it, then you're going to heat treat it, right? So relatively easy, again, minimal warping, minimal cracking, which also means minimal residual stresses from non-uniform cooling, thick sections, no problem. I mean, again, Marujan steels are the rock star of the steel community. So where do we use them? We only use them where we need them because they are insanely expensive. And so you see them extensively in aerospace, our solid rocket motor casings, aircraft landing gear. These are all pretty common places to see Marujan steel. So we need really high strength, excellent strength to weight ratio. And then we also need good ductility. And so when we need all those things in one, Marujan steels are a good pick. It helps when the cost is not prohibitive. So, when you're building solid rocket motor casings, they don't really worry about the bill for the materials as much. We also see them used for tools and dies. They come in different grades. And so you can see, again, we can go all the way up to 350 KSI. This is yield strength in MPa, and I just translated it to KSI over there. Yeah, pretty cool material. All right, so we've got all our steels out of the way, and now we're moving on to talk about cast iron. And cast iron is an extremely useful material, and essentially we're just going to add a whole lot more carbon. So significantly more carbon than is in stainless steel. It's typically more than 2.14 weight percent, but we can go all the way up to, generally we're going to be between 3 and 4.5 weight percent in most cast irons. And so if you think about where that actually puts us on our diagram here, what we realized is that actually iron carbide is not a equilibrium phase. And so our iron carbide will actually can be made to decompose. It's metastable, and it'll decompose into just pure carbon, graphite, and iron. And so one of the things that we often add is silicon. And so silicon is a graphitizer. It tends to encourage the formation of this graphite. It tends to encourage the degradation or the decomposition of iron carbide into iron and graphite. So this is one of the reasons why when you're looking at especially high carbon steels, a lot of times they're going to be very particular about limiting the amount of silicon in there. Because if you want your carbon to stay in a solid solution and not, if you want to form iron carbide and you don't want to form graphite, then you got to be careful how much silicon you put in there. The slower we cool, the more we're going to favor graphite formation as well. But if you add enough silicon in there, since it is a graphitizer, you're going to actually form graphite instead of iron carbide. So different types of cast iron. Gray iron. Gray iron, the microstructure consists of ferrite, which is the white stuff here, pearlite, which is hanging out in there, and it'll be a mix. Sometimes you'll have a more pearlitic microstructure. Sometimes you'll have more ferritic microstructure, and then all these dark things are graphite flakes. So the form of the graphite. Generally, when we're classifying cast irons, we're really paying attention to what form the graphite takes. So the reason it's called gray cast iron is because when you fracture it, and it does fracture, there's very little ductility, the surface appears very dull because all of these flakes kind of are on the surface and they don't reflect light very well. It's going to be relatively weak when compared to our typical carbon steels. It's going to be very brittle in tension. It'll perform better in compression, as most brittle materials do. So these sharp flakes, right, they're going to be stress risers. So you have these very sharp graphite flakes. It's not surprising that it's going to be a relatively brittle material. So we still use it a lot. We're just not going to use it necessarily in high stress applications, right? Remember that if we have a low strength material, all it means is that we're just going to have to increase our load bearing cross sectional area. It just means that whatever we're building out of is going to be significantly larger, heavier, thicker. And that may be okay. The upsides of cast iron are that it is very relatively cheap, on the order, I would say, of our carbon steels. We can actually allow a little bit more junk in there, so the chemical composition we don't have to control as tightly. But the big thing is that the addition of the carbon actually lowers our melting point, and so it stays liquid at a lower temperature, it becomes liquid at a lower temperature. And now this is important when we're talking about castings, right? Because if you're running a casting operation where you are melting down your metal and then pouring it into some mold, right? And the mold can be pretty extensive, right? How hot you heat your molten metal before you cast it is going to be dependent on what your mold looks like. So you need your metal to flow into all the little spaces of the mold before it solidifies. And as a result, having lower melting temperatures saves us a lot of money and lets us mold more complicated structures than if we were talking about a cast steel. Yeah. So gray cast iron, it's got some really good properties. Again, not great mechanical properties in terms of its ductility, but great vibrational damping. It's got high wear resistance, right? And it's very fluid in the molten state. So all those things kind of combine, and the fact that it's the least expensive, it gets used quite a bit. One of the places, we've already talked about this, one of the places you see it is for brake rotors. And so there you think, wow, that's kind of the perfect material, right? We're not talking about crazy amounts of stress it's going to see. And we need good vibrational damping to deal with the fact that our rotors are not always turned nice and smooth. And we're also going to need good wear resistance because our brake pads are going to be clamping onto, and we're going to be generating a lot of heat. And so the nice thing about graphite is it's a lubricating agent. So these graphite flakes just serve to lubricate the surface and give us good wear resistance. Our ductile iron, ductile cast iron, or sometimes it's just called DI, is going to, instead of having graphite flakes, it's going to have graphite nodules or spheres. And so the idea here is we just add a pinch of something that favors the formation of spherical graphite over flake graphite. And those two elements that are typically used are going to be magnesium and cerium. So cerium being a rare earth, you can add it in smaller quantities. It just tends to be more expensive. Yeah, and so that's what we can add. We see higher strengths, so we generally see higher yield strengths on these. And more importantly, we see significant ductility on a lot of them. Some of them we don't see a ton, but generally we're seeing higher ductility than we would in a gray cast iron. And so, you know, in terms of, I know the water utility, they've got a lot of cast iron in the ground. They've got that's gray cast iron, and they've got a lot of ductile iron in the ground. And all the new stuff is ductile iron. So the old pipes in the ground, water pipes in the ground, are cast iron, and the newer stuff is going to be ductile iron. But neither one of these is as strong as steel. So, you know, for our water transmission mains, where we're dealing with higher pressures, those may be actually made of steel. And the distribution lines that are lower pressure are going to be ductile iron, and typically are going to be ductile iron and cast iron. So yeah, white iron. White iron, it's got low silicon, and generally we're actually going to form mostly iron carbide. And this it's called white iron because if you fracture this surface, the iron carbide reflects really brightly, and you get this really reflective surface. So in almost every gray cast iron casting that you have, there's a little bit of white iron in there. And it usually occurs right on the outer surface where the molten metal hit the mold. So when you cool gray cast iron really quickly, you'll form some percentage of white iron because that iron carbide doesn't have a chance to decompose into the flake graphite. Yeah, we can further process this into malleable iron. And malleable iron, essentially we just heat up our white iron, which was cooled very quickly, and it decomposes. And in this case, the iron carbide decomposes generally into these sort of graphite rosettes, sort of these blobs of graphite. And that's what the dark stuff is here. And as a result, the white cast iron we generally use for wear resistance. It tends to be really hard, and it stands up to you know, basically rubbing and friction between different parts. But our malleable iron, right, is more when we care about the mechanical strength and ductility. So for applications where we care about the ductility, you know, we're going to choose yeah, malleable iron. Compacted graphite iron, this has vermicular or worm-like graphite. And it just, basically we're going to add a little bit less, it's kind of right in between gray iron and ductile iron. We add less magnesium or cerium than ductile cast iron, and as a result we get, you know, kind of some, you can see there's a few spherical graphite nodules, and then it looks like kind of these worms, they just kind of look like rounded graphite flakes. And so it has some properties that we like. It has lower corrosion or oxidation at higher temperatures than ductile or cast. The mechanical properties are not fantastic, but again, they kind of fall right in between gray and ductile cast iron. Yeah. So if you're going to be using these at high temperature, or if you're going to be using them in high temperature applications, you might go with compacted graphite iron because you're going to get better corrosion resistance or oxidation resistance. So this gives you an idea of sort of what range you're in, and what we form depends on how much we added of other things and then what our heat treatment looks like. So this gives you an idea of how you form the different types of graphite, or yeah, the different types of graphite, how you form the different types of cast iron. Because technically white cast iron doesn't have graphite in it, it just has iron carbide. All right.